So this video is going to focus much more intensely on epoxides, and I've already talked about how you make epoxides. If you take a double bond like this and you add to it metachloroperbenzoic acid, this reagent, then the outcome is going to be that you make both flavors of the epoxide, which is to say the one where the oxygen is up and the methyl is down, and also the other enantiomer. So this, of course, is going to have the oxygen facing back away and the methyl up as the other enantiomer. But in addition to making this, we are now going to be interested in the ways that we can use this synthetically, and there's really going to be two general categories that I want to focus on, which is epoxide opening under acidic conditions and epoxide opening under base conditions. And those two are going to operate under different general rules. So that's what we're going to focus on. But as a quick review, know that this is the right reagent, if you will. So that's metachloroperbenzoic acid, and the reason why I have shown it to you before is to highlight how the mechanism of this works, and there was really 2 points that I was trying to make there. The first is that this has to be delivered, the oxygen that ends up in the epoxide has to be delivered from the same face of the double bond, either the top or the bottom, but it happens all simultaneously, it all happens at once. The other point here is one that I've highlighted a couple of times now in the magic videos, and that is that oxygen-oxygen single bonds are really, really weak. So the driving force for this entire mechanism really is breaking of this bond. But I started it out by saying, hey, this double bond can be nucleophilic and can push electrons onto that oxygen. But again, the driving force is the breaking of the oxygen-oxygen single bond. For bookkeeping's sake, I say that those electrons go to make a double bond, and that causes these double bond electrons to come over and pull off that hydrogen. And because of that, this pair of electrons is now free to go somewhere, and the place with the most delta plus when all is said and done is this carbon. And so the mechanism that I've shown for you before, and I'm highlighting again, says that the double bond serves as a nucleophile, mostly because the oxygen-oxygen bond is so weak. But as this double bond attacks, that leaves behind an area that will be delta plus at this position. So you need to have the oxygen nearby donate electrons, and if we pull off that hydrogen simultaneously, because this is all organized the right way, all of that happens in one step. There is your product. Of course, if this group comes from the bottom face of the double bond, then when the double bond attacks, the oxygen ends up back down and the methyl ends up forward. So you make both. You make the enantiomer as drawn when I have this as the organization of the transition state and of the mechanism, but if the group comes from the bottom, then you make the other enantiomer. So that's how you make them. But now when you open them, there's going to be different rules depending on what happens, and we'll need to go into that in a little bit greater detail. For now though, let's assume that we have sulfuric acid as the acidic reagent, and we're going to run this in, say, methanol, and we will consider what the mechanism is that leads this material onto products. And for base purposes, let's not do anything fancy. Let's just add in sodium hydroxide, and we'll choose some non-nucleophilic aprotic solvent. So the solvent's not going to be involved, it's just there as a spectator, and we will consider the mechanisms of both of these.